We are going to do a problem. It's a calorimetry problem with solutions. I'll be honest, I think this is one of the hardest calorimetry problems for students, and it's because of one thing: you have to add masses. I'll show you where. So here's our problem. We're told that we're going to create a solution mixing sodium hydroxide and hydrochloric acid. So I wrote down everything that was given in the problem. We have 200 mils of a 0.4 molar sodium hydroxide, 200 mils of a 0.4 molar HCl. Now in the problem, it said that the initial temperature of both of these were 25.1 degrees C, so I wrote T initial for both of them, and that the final temperature, so thermal equilibrium, where these come into a final highest temperature after they're mixed, 27.78 degrees C. They ask for enthalpy change for 1 mole of the acid, and then give this little parenthesis side note of, hey, assume that the density of the solutions, that it's 1 gram per mil, and the specific heat of the solutions, that's 4.2 joules divided by gram times Kelvin. All right, where to begin? So we're thinking about energy transfer. That's always where your brain goes when you're asked for heat or enthalpy. So I have these two solutions, I pour them together, the temperature goes up. Here's what happens. The reaction between the sodium hydroxide and the hydrochloric acid, that reaction releases energy, and it causes the whole solution to increase in temperature. So the reaction is exothermic, releasing energy, and the solution is endothermic. The temperature goes up because it absorbed energy. So how do we write this down? It's going to be the reaction is exothermic, okay? It releases the energy when these the acid and base come together, and that's going to equal the energy absorbed by the solution. Notice I do SOLN as my abbreviation. Now, why I set this equal to each other? Because of the conservation of mass. The amount of energy lost always has to equal the amount of energy gained. So I write them equal. Now, sometimes you'll see it written like this. It would be Q solution plus Q reaction equals 0. And that means the amount lost plus the amount gained always is a net 0. For my brain, it works easier if I think about the amount lost has to equal the amount that's gained. Same formula, maybe just a slightly different way of looking at it. So here's our formula. Now we are looking for enthalpy. So let's write down a reminder of what's enthalpy. That's delta H. And delta H is kilojoules per mole. Kilojoules, that's energy. So really delta H is just Q divided by moles. So if you're asked for enthalpy, you first have to find heat, the energy released in this particular situation. We've got to find Q. That means that right there, Q of the reaction, that's my unknown. So I'm not going to break that into the formula. Students will always ask me, Mrs. Lobb, when do I use Q or find Q? When am I using CM delta T? If they want enthalpy or heat, you don't break that apart, okay? Because that's the answer. That's the answer. So we're going to have the energy released by this reaction, negative Q of reaction, equals CM delta T. Okay, now let's take a look at our CM and our delta T. Well, I can see the delta T easy. Here it is. Because this is one solution, we have the initial and the final. What you would do in the lab is you would take the two solutions and set them on the counter and let them come into thermal equilibrium with the room so they have the same temperature. Then you mix them, get that highest temperature, or if it's endothermic, it would be the lowest level temperature. Get your final temperature. So that's easy. We've got delta T. Now specific heat, they gave it to us. Here is the hard part that you have to know. When you have a solution, you have to add the masses. You have to add the masses because this is coming into one new homogeneous substance. You have to add the masses. Now they gave us density, and often you'll see this that for solutions, they'll kind of do this fudge where they'll say, hey, the specific heat's the same as water. They'll say it's 4.2, and they'll say, oh, for this solution, it's the same density of water, 1 gram per mil. Great, makes it easy for us. So just a reminder, if I have 200 mils and 1 mil weighs 1 gram, that means I have 200 grams. So I could really come back here and write gram. Those are just grams right there. Okay, if I have 200 mils, I've got 200 grams because of the density, 1 gram per 1 mil. Okay, let's plug in. So negative Q of the reaction equals the specific heat, 4.1. And this is going to be joules divided by gram times. Now, that says Kelvin. I'm going to go ahead and change that to degrees C. And here's the reason why. When you subtract final and initial, the magnitude change for Kelvin and Celsius are the same. So because we're doing change, I can actually replace that with degrees C. You could use the Kelvin and the degrees C because it's associated with change. You can use those interchangeably. Now, if you're looking at just one temperature, like in gas laws, no way. You have to use Kelvin. But when we're doing change, you can use them interchangeably. Okay, times, now here's the part, be careful. 200 grams plus 200 grams. We combine these into one new mixture, one new substance. So you have to add. I'm going to write this down. Be so careful. Add the masses. Add the masses. When you're making a new solution, so it could be a salt into some sort of aqueous solution or a salt into water, or if you're adding two solutions, you have to add the masses. Common mistake. So add the masses times our change in temperature. So final temperature, 27.78 minus 25.10 degrees C. Let's look at our sig figs really quick. Order of operation, let's do the subtraction first. We are going to have 27.78 minus 25.10, and that will give us, let's see here, 2.68, and we truncate at the hundredths place. So that means I've got 3 sig figs. I'm going to make this mental note. I've got 3 sig figs from this, 2.68 degrees C, and that's a positive number. So now we multiply everything, and when we multiply, we are going to get negative Q of the reaction equals 4,502. Let's look at the units. Grams, cancel, degrees C, cancel. That is going to be joules. So what did we find? If, very specifically, I mix 200 mils of 0.4 molar, 200 mils of 0.4 molar, mix that together, it is going to release 4,500 joules. Now, if they just wanted the amount of energy released in this very specific situation, if they wanted heat released, there's your answer. And by the way, I could do Q of the reaction equals negative 4,500 joules. Remember, I had 3 sig figs times 3 times 2. I ended up with 2 sig figs on this, 4,500 joules. They didn't ask for Q though. They asked for delta H. And you'll find in problems, they usually ask for both. They'll want to know the heat released, and then they'll want to know the enthalpy. Now, when they ask for enthalpy, they have to tell you for which one. They have to tell you, do they want it for substance A or substance B? In this case, for the base or the acid. And they specifically asked here, what's the enthalpy change for 1 mole of acid? Interesting, because we have the same volume and molarity, we're actually going to come up with the same answer. I have seen AP ask for delta H without specifying acid or base, but they set it up that it would be the same because you have the same volume and the same molarity. Okay, again, if I want delta H, kilojoules per mole, it means I have to find the mole. I found the kilojoules, okay? Got my energy, my joules, but now I have to find moles. So let's do that. We're going to take our hydrochloric acid. I have got 200 mils of a 0.4 molar. So that means for every 1 liter, we have 0.4 moles. Ooh, liter. I've got to put this into, I've got to put that into liters. So just divide 200 mils by liters and we get 0.2. liters. Great. Now the units cancel. Be careful. Be careful with your units. Units will always tell you what to do. So that cancels, and we are going to get 0.08 moles of HCl. Okay, let's convert this to kilojoules. I'm going to divide this by 1,000. We've got 1,000 joules in 1 kilojoule will give us 4.502 kilojoules. Now we can divide. So delta H, remember, this is going to be kilojoules per mole. I got the kilojoules from finding Q, and I found the moles by using the volume and the molarity right here. We have negative 4.5 kilojoules, there's my 2 sig figs, divided by 0.08 moles. That would have been 3 sig figs, but we'll end up with 2 sig figs anyway at the end. Okay, divide this and we come up with negative 56 kilojoules per mole. Notice this negative, I just took the negative right here and I brought it over there. Since the Q was negative, so I brought it down here. And there's your answer. So what did we find? We found that when you react the hydrochloric acid with the sodium hydroxide, for every 1 mole of that HCl in this reaction, it is going to release 56 kilojoules. There's your delta H, kilojoules per mole. We had to divide by the moles that they told us, in this case the acid. And then remember Q? The Q came from the reaction released energy, and it was absorbed by that solution. Let's see, there were a couple of other items that I wanted to make sure that I shared with you. Touched them all. Good job.